afternoon. Chris Weeden. I'm a Systems Engineer, Technical Pre-Sales for WekaIO, and this may all be marketing, but we've got lots of technical information. A quick introduction. We're kind of the new kids on the block. We're a modern-day storage solution for the modern hardware that's available. We were founded by the gentleman that created the XIV product for IBM. We've been around since 2013 developing the file system. We're a software-only solution. We work with partners to deliver the infrastructure. We have a large amount of intellectual property within the product, a number of patents filed, and we've grown very quickly with a lot of accolades already. What is it we do? We aim to be the world's fastest parallel file system for technical and AI compute workloads. And we can provide access to the data on-premise or in the public cloud. You can run the file system on bare metal or in the cloud. We have the traditional markets that you would associate with high-performance computing workloads. We're seeing particular traction in the top three. Genomics, where they've got their huge data sets but have a high-performance requirement as well. We have a large installation at Genomics England. 1.5 petabytes of NVMe flash, and about 20 petabytes of object store as a tiered solution. Machine learning, again, we've just had the talks about the workloads that are pushing GPUs to their limits and driving up processing capabilities. Huge demand for data input quickly into those servers. We have about 10 companies globally doing autonomous driving with machine learning, gaining great traction. Our ludicrous company in the US is one of our untouchable or unspeakable companies for people who have ideas. Algorithmic trading, we provide a very low latency access to data, so the financial markets are able to use a shared parallel file system to access data that before they would rely on block devices to deliver the speed without being able to share that data easily or widely. Some of the customers we have already have been generally available since late 2017. So again, very fast adoption of the technology within the industries. Quick overview of how the solution ties together, what it looks like. We have our customers with their data sources of various types. And they will have a compute infrastructure to compute against those data sources. They could be Linux servers with just CPUs or GPUs. We have a client driver that sits within the Linux clients to allow them to talk our Extreme protocol. But we also export the data using NFS and SMB for other non-Linux connectivity. These clients are connected over a high-performance network. We're typically sitting on 100 gigabit networks, whether it's in Ethernet or InfiniBand. And we have a collection of servers providing the NVMe infrastructure for our data to strike across. These servers, we show them here as dedicated storage servers, but they could be converged within the computing platform itself. We rely on industry partners to provide the infrastructure. We have a number of reference architectures where we've qualified their platforms, and we have extreme performance density. Again, with the NVMe devices, we can also provide huge capacities within small physical footprints. We start at around 35 gigabytes per second from 4U, all the way up to around 400 gigabytes per second on a single rack. And as we're moving to 200 gigabit networks, we expect that number to virtually double. But NVMe is expensive, and you don't want to keep all of your data as you have very large data sets on NVMe. So we provide automatic tiering to a secondary tier using the S3 interface. So we provide access or the ability to tier using user-defined policies from NVMe into an object store. And that could be an object store on-premise, and again we have qualified solutions with industry partners, or it could be in the cloud. Currently we work with AWS, we run natively within AWS, so again you have the option of cloud bursting with the file system to improve performance in the cloud itself. Both of those tiers are infinitely scalable. So we can run up to 64,000 NVMe servers. We're looking forward to a customer testing that theory. And object stores designed to grow to the exascale. We present all of that as a single namespace. So the clients don't know which tier their data lives within. They have a view of all of their data from a file system mount, and POSIX file system access. We lead on performance, and we claim to be the world's fastest parallel file system, and we have public benchmarks to back that up. One of the suites that we ran was the SpecSFS benchmark suite, and it's an interesting benchmark. You don't just run it and get your maximum number, you set yourself a target and hope you get there. And if you don't, you have to wind your aspirations in a little bit and have another go. When we attacked this, we looked at all the top numbers for the various different benchmarks and set ourselves a target of being twice as fast as the next best solution. We were able to achieve that in most cases. The outlier is the software build. On the day we released our numbers, NetApp released a new set of numbers, so we have a new target to chase. But our response time was significantly lower. Our test took about a third of the time to run, on about, I can't remember the numbers, significantly fewer clients. I'll whiz through these. It's, the shape of the graphs is really what's important here. The other thing that's really important, not only did we have the great results, but we were the only vendor that ran those benchmarks, all of their benchmarks. So we didn't cherry pick the ones that suited our solution well. We were able to run all of the tests on the same file system with no tuning in between. So again, the file system is very capable of handling the mixed workloads that these benchmarks stress. So it's a database test. Again, you can see where some of the competition hit their limits, whether this is a metadata bottleneck of some sort, whichever. We were able to maintain our consistent low latency. This is on 24 super microservers with NVMe only. This is not tiering at this point. An EDA benchmark. So again, a different workload, but able to maintain that steady low latency as others run into particular bottlenecks within the solution. Streaming video, support for up to 7,000 simultaneous high definition video streams. VDI, so virtual desktops. Again, maintaining that low latency so the desktops will have a really good response time. The users will feel like a local file system. We also had an independent test run by HPE to look at how we can support GPU workloads. And we compared ourselves to accessing the data set over the network, parallel file system with WekaIO, accessing that same data set from a local NVMe array, and accessing that data from within DRAM within the box itself. As you can see, when you increase the load to 2 GPUs, all are able to keep up with the I/O demands. As we increase the CPU capability or GPU capability, the I/O demands exhaust the local NVMe array, and finally, we're only just beaten by the DRAM in the box. And we have performance improvements that have narrowed that gap even further. So those are the bold claims to get the attention. We're going to show you a little bit of how we were able to achieve it. So this is the fun stuff, the architecture of the solution. We are a software-only solution. We install our software into containers. So software lives in containers in user space on the NVMe servers, and we show here a dedicated server platform with client platform as well, but again, these could be converged. We try and avoid the kernel wherever possible. We don't want to sort of be at the request of the kernel's context switching and interrupt modes, because that introduces the latency. So we employ Intel libraries that allow us to talk directly from user space to the hardware, whether it's DPDK for the network or SPDK for the NVMe themselves. We're also addressing the NVMe directly for block allocation, so we're not using an interim file system. So there's no file system that's designed for spinning disk within our solution. It's all been designed dedicated for the hardware available today. We have the software nodes, and we can apply resources to those nodes to improve the performance of the I/O capability. So if you're in converged mode, you can tailor the amount of resources you wish to apply to I/O versus compute. By allowing us to bypass the kernel, we can maintain extremely low latencies. We assign cores to these processes, and we keep those cores busy all of the time in a poll mode. So again, it's not interrupt driven. We are constantly asking those services, have you completed the work? Are you ready for the next piece? So we can keep those latencies really low. And And you can see the performance of modern networks, if you use them efficiently, the cost of moving 4K of data across a network is negligible compared to the time it takes to read from very fast NVMe already. So now we get this notion that data locality, even though we've seen it being very important, keeping the extreme data memory-driven local to the CPUs and GPUs, when you're accessing data from physical devices, the location is less important. We can move that data really quickly over the network and very efficiently. The networking stack is doing an RDMA-like process. It's our own stack. So again, we're not bound by the legacy kernel stack for accessing the network. We can drive this throughput and this performance. I've got 5 minutes, so I'm going to have to speed up a little bit. We fully distribute the metadata across all of those servers. And even within a single directory, multiple metadata managers will be participating in that lookup. So we use hashing lookups, hashing algorithms at the client to talk directly to the software node responsible for the piece of data you're interested in, so we can distribute the metadata. And this provides us with great scaling and maintaining that scalability and low latency as you continue to increase load and scale on the system. We could take the data in the NVMe, so we do an erasure coding-like protection, but maintain performance while we do it. We also have end-to-end checksums. So every piece of data, every 4K has a checksum that's read as data is read back from the system, so we can eliminate silent data corruption. The automatic tiering from NVMe to S3. So we have very simple, user-definable policies that allow us to provide this huge capacity there, whilst providing a high-performance window into that data, and that window should be large enough to cope with your hot data that you actively compute against. You have a very simple solution that allows you to scale to many exabytes, a very cost-effective solution. Very fast rebuilds, I won't dwell on that one, it's parallel rebuild, any rebuilding data. We have snapshots in the system. These are zero performance penalty for taking a snapshot. It's instantaneous. We do a redirect on write rather than a copy on write. But we also have this great feature of a snapshot where we can take a snapshot and we can bundle it with a manifest that describes the file system layout and push all of that into the object here as a backup of your file system. We can use that backup to rehydrate a new file system in the event of a disaster recovery or just as a backup mechanism. So again, with the tiered solution, you no longer need to worry about backups and disaster recovery in a traditional way. Take a snapshot, push it into the object tier, that gets replicated by the object tier, and you have safely stored that data. You can use this mechanism also for bursting into the cloud. So it's an object store accessed by S3, take a snapshot, we can push it into AWS today, but we're working with the other vendors. And you can spin up a Weka or FS cluster in the cloud and recreate that file system from the snapshot data, compute against it, take a new snapshot of the new results and push that back to your on-premise. So it gives customers the flexibility to do work on-prem and burst into the cloud where necessary. Great security features, so we follow the Unix permission model, but we have extended POSIX ACLs. We support data encryption in flight and at rest. We tie into customers' KMS, we have a lot of that, and Active Directory support, but also multi-tenancy, where we can evolve administration capabilities to a tenant, and the admin has no access to the data itself. So we get lots of features that allow you to provide very large systems and share those out between multiple tenants. Administration is very easy. Because the file system is so capable, there's nothing to tune. So again, it's just a case of creating these virtual file systems that strive across all of the resources to deliver that high performance capability, and we have all the other features to look after the data. We have the CLI as well, so everything can be scriptable. And we have a 24/7 follow the sun model to support, which already is garnering great feedback from customers in the field. I think just about there. Thank you very much.
Thank you, Chris.